Hey everyone, and welcome. Today's explainer is going to clear up a highly confused topic in electrical short circuits. Honestly, it's one of those things that trips up not just engineering students, but even seasoned professionals out in the field. Today, we're tackling the ground fault fallacy.
Okay, let's dive right into this. Here's our roadmap for today. We're going to start with the ground fault fallacy itself, then define double line to ground faults, and contrast those with separate single line to ground faults. After that, we'll uncover the metallic path danger, compare the fault types, and wrap up with the critical impact this all has on IT grounding systems. So, starting with Section 1, the ground fault fallacy, let's talk about why this is such a confused topic.
There's a pretty widespread misconception out there in the electrical engineering literature, and it basically comes down to a misunderstanding of how faults actually manifest in the real world versus how we categorize them on paper. So let me just ask you this directly. Are two ground faults the same thing as a double line to ground or DLG fault? I want you to really visualize the physical setup of a power system here. Think about the wires, the phases, the ground. Now, while it might sound like a trick question, the answer is a resounding no. You see, fault behavior depends entirely on spatial mechanics, and confusing these two concepts can lead to some really serious errors in your system protection.
Moving on to Section 2, double line to ground. Let's get into the exact spatial mechanics of this specific fault type.
Precision is absolutely crucial here. A true double line to ground fault happens when two phases come into contact with both ground and each other. Well, actually, they have to hit at the exact same physical location. I really want to emphasize that part, the same physical location. That precise coincidence in space is exactly what the electrical literature classifies as a true DLG.
Because these two separate phases are literally touching each other and the Earth at that exact same spot, boom, it creates a direct phase-to-phase short circuit. The fault current doesn't have to travel across the network at all, it just seeks the path of least resistance right there at that single point. The short is immediate, it's localized, and it is extreme.
Okay, Section 3, separate single line to ground faults. Let's see how a shift in geography changes this entire scenario.
Now this is where that distinction becomes absolutely critical. Two separate single-line to ground faults occur when two separate phases experience ground faults at completely different physical locations. I want you to visualize this spatially right now. Imagine one fault happening on phase A at a substation, right? And then a completely independent fault happening on phase B, literally miles down the line. They are geographically and physically separated.
Interestingly enough, standard electrical literature doesn't really give this a fancy acronym. They're simply independent events that just happen to co-occur on the same system. And because they happen at two completely distinct locations, they are not initially connected in any way, shape, or form.
Which brings us to Section 4, the metallic path danger. This is where we really need to highlight a major engineering hazard. Let's walk through exactly how these separated faults can escalate. Step 1, you've got your two independent ground faults occurring at different locations on different phases. Step 2, instead of the fault current safely dissipating into the Earth like it should, a metallic return path connects these two distant faults. And Step 3, since electrical current always seeks the path of least resistance, that highly conductive metallic connection suddenly turns the whole situation into a dangerous, severe double-phase or line-to-line fault. The physical distance completely stops protecting the system because the metal has linked the two phases together.
Section 5, comparing the fault types. Let's place these concepts side by side to make sure this distinction is crystal clear.
And this brilliantly illustrates the core differences. Physically, a DLG fault happens at the exact same location, while separate faults are, well, physically divided. Electrically, a DLG is an immediate, localized, phase-to-phase short. Separate faults, on the other hand, act independently to ground, unless, of course, a metallic path bridges them, escalating them into that severe line-to-line fault we just talked about. Understanding this difference is literally essential for designing proper system protection protocols. All right, final section, Section 6, IT grounding system impact. Let's pivot to a real-world application where this theory meets critical safety standards. In isolated, ungrounded IT systems, this distinction isn't just theory, it's vital for system survival. A first ground fault is usually tolerated because the system doesn't have a direct path to ground, so it can just keep running safely. And that is exactly why we rely on installation monitoring devices, or IMDs, to alert us to that very first fault. But if a second fault occurs on a different phase before we can fix the first one and a metallic path links them, it creates a catastrophic short circuit. The presence of those metallic return paths makes understanding this distinction vitally important for protecting your systems. So if you take nothing else away from today's explainer, take this and burn it into your engineering memory. A double line-to-ground fault is absolutely not the same as two independent ground faults. If this explainer finally cleared up the ground fault fallacy for you, please hit that like button, subscribe, and drop a comment below with other confusing topics you want us to tackle next. Keep learning, stay focused, and I'll catch you in the next explainer.